Class? Okay, so we're going to talk about magnetic materials. So, say we have a magnetic field, and we talk about magnetic fields as arising from moving charges, or electric currents. Now, the most familiar example of magnetism is what we call a bar magnet, or I think everyone's familiar with those. So let's say we put a bar magnet in this magnetic field. So a bar magnet, it has a north and a south pole. Now, these are called poles for historical reasons. The first use of magnets, they discovered a long time ago that magnets, you could design a magnet, like a thin needle or something, that would always point to the north. And so it points to the North Pole, so they call it poles. Now, we could just as well call them, like the North Pole, say, a positive magnetic charge, and a South Pole as a negative magnetic charge. If you have a bar magnet, if you have a north and a south pole, if you look at the magnetic field lines, it looks just like what you would get from having a positive and a negative charge. And when you have a positive and negative charge separated by a small distance, that's called a dipole, like an electric dipole. And so again, kind of looks just like a bar magnet. Now, for historical reasons, we call these poles. Now, we'll learn later that in nature, you'll never actually find a north pole or a south pole in a magnet. If you were to cut this magnet in half, you might think, okay, there's a north pole on this end and a south pole on this end, so if we cut it up in half, we'll get, just the north pole by itself and the south pole by itself. But that doesn't happen. When you cut it in half, it forms two dipoles. And you can cut this in half again and again and again, and ultimately you get down to an atomic level where an atom itself acts like a dipole. And so as far as we know, there's no such thing as a magnetic monopole. So mono meaning one, so you'll never find a magnetic monopole in nature. Just as a note, if you do happen to see one, definitely, don't lose it. They've been looking for them for decades. And the reason why they look for them is the theorists believe very strongly that magnetic monopoles do exist. Because if they do, that would explain certain things that we don't have to worry about in this class. So there are good reasons, although absolutely no evidence, to believe that magnetic monopoles actually do exist. But so far, absolutely no evidence of that. So as far as we're concerned, the smallest unit of magnetism is a dipole. They always come north and south poles together. But again, if you think of a north pole as like a positive magnetic charge, and here's our magnetic field, if you put a positive charge, it's going to, the forces, it will cause this bar magnet to rotate and line up with the magnetic field. Just like if you have an electric charge, if you have a positive charge in an electric field, so let's say this is the electric field, force on a positive charge is going to be the same direction as the electric field. Where if you have a negative charge, if this is your electric field, the force is going to be in the opposite direction. So if we look at the north pole as a positive charge, that's going to be to the right. South pole is a negative charge, force is going to be left. That's going to cause this magnet to twist and line up with this external magnetic field. Okay, now mention that we can go all the way down to the atomic level, and atoms themselves act kind of like bar magnets. I think I mentioned this a little bit before, because ultimately the origin of magnetic fields is moving charges. And so if you have the nucleus of an atom surrounded by electrons, this is a moving charge. We think of the electron as orbiting the atom. So we have a current, even though it's a kind of a discrete charge, at least in this model. That should create a magnetic field. And there's also an intrinsic magnetic moment for the electron and also for the elements that make up the nucleus, so like protons. And so, we don't want to get into too many details because magnetic fields are vectors, but there's several different contributions. One, we have the orbiting electrons. And also the electrons themselves, it's called electric spin. You picture it like a ball of charge that's spinning. That should have magnetic effects as well. And also the nucleus does. And these are all vectors, so they kind of add up. They can cancel each other out or partially add up. So what's actually going on is fairly complicated. But to a good approximation, every atom can be seen as a bar magnet. So let's go back and say we have just a piece of matter. Could be anything. Let's consider something like a metal. Just an element. Here, let's say gold. Or let's say aluminum. And I say that because aluminum is not normally something we'd associate with magnetism. Okay, so every atom acts like a tiny magnet. So if we have this block of aluminum, why doesn't this act like a magnet? And the reason is, if you look at an atomic scale, we can represent each atom as like a little bar magnet. So let's say the arrow points to the North Pole or something, except they're totally randomly oriented. And so it's just the randomness that causes no net effect. They're vectors. And so they just cancel each other out. And so this aluminum does not have any magnetic properties on a large scale. So you can think of it as made of just tons of magnets, but you throw them all together in a totally random way, and they cancel each other out. But now if we apply an external magnetic field, what happens, we looked at what happens if you just have an ordinary bar magnet. Here, we'll represent it the same way. It's going to cause it to rotate and line up with this external field. And this is a property that is common to many materials, and this is called paramagnetism. So basically what we have totally random. Maybe I should draw two pictures. Yeah, I'll draw two pictures. So here we have something that's totally random. Yeah. Tons of individual magnets, but they're randomly oriented. And then if we apply a magnetic field, we get at least, now they're not necessarily all going to just line up with this external field, particularly if the external field is weak. But they will at least tend to point more in the direction of the external field. So maybe some will still point a little bit in the opposite direction. But overall, they're going to be pointing more to the right than to the left. So let's say it looks something like this. And so the effect is, so this is called paramagnetism. and it's called para for parallel. What this does is, here the internal field is 0. So we've got all these magnets, they cancel each other out. But now because the atoms kind of line up with this external field, they create an internal field that points in the same direction as the external field. And so that is called paramagnetism. And this is common to many elements. To some extent, you could expect this in the odd numbers on the periodic table. That's not like a die-hard rule, but you'd expect this more from the odd numbers. And the reason why is if you have an even number of electrons, they tend to pair up in ways that cancel each other out. So if you have an odd number, there's one odd electron that that's not canceled out, so it's free to rotate and line up. But again, not like a die-hard rule that you can just always count on, but more just a tendency. Okay, so paramagnetism. It creates an internal field that lines up with the external field. And so the magnetic field inside this material, or in the area around it, is much stronger now. So if you have an external field, and now you place a material there, a paramagnetic material, then you have a stronger magnetic field. Now, another important thing about paramagnetism is what happens if we remove this external field. It goes back to this. The internal field disappears. Again, these you can think of these as atoms that are kind of lined up in this direction. But if you remove what's causing them to line up, they're still, the atoms on an atomic level are oscillating, and they kind of hit each other, exchange energy, and that randomizes things. So they'll go back to being just demagnetized very quickly. So this internal field only exists when the external field exists. Okay, so that's the basic idea behind paramagnetism. Now next we want to talk about something called diamagnetism. So I won't draw the atoms here, but say we have an external field. And what happens for a diamagnetic material, actually this happens for all materials. All materials have this effect of diamagnetism. But what happens is it creates a magnetic field that opposes the external field. So the field inside will be weaker. So you might have heard that term diametrically opposed, like exactly opposite. That's why it's called diamagnetism. Okay, so diamagnetism, the internal field is exactly opposed to the external field, and every material has this property. So what about a paramagnet? Well, if we have a paramagnetic material, it's going to have both paramagnetic and diamagnetic effects. They happen for different reasons. Diamagnetism, I don't want to even try to explain why that happens. It ultimately has to do with quantum mechanics. Like, it can't really be explained without quantum mechanics, so let's just say this is a common property for all materials. But it's usually a pretty weak effect. So if you have both paramagnetic and diamagnetic properties, very often the paramagnetic effect is going to win. And so yeah, for those materials, we just call them paramagnets. So this diamagnetism phenomenon is still happening. It's just overwhelmed by the paramagnetic effect. Okay. And just like before, if we remove this external field, it just goes back to this totally unmagnetized state. Now, again, we could talk about magnetism, there's entire books written on just magnetic materials. So we're just going to talk about, very basic concepts, and we're going to mention 3 properties. The next is ferromagnetism. And this, you want to think iron. I think it's ultimately comes from Latin, like ferrous or something, iron. But say we have, if we look at iron, there's a few other, I think nickel kind of does this as well. So if you look at this on a, you can like magnify and see what's going on. Well, not on an atomic level, but a ferromagnetic material, like iron, it has these regions called domains, where in a particular domain, all the atoms line up the same way. But in different domains, they're pointing in different directions. And so overall, if you just have a block of iron, it's probably not magnetic. So certain regions are magnetic, but the adjacent region could point in a completely different direction. And remember, magnetic fields are pretty weak. Like we looked at this example. If we put a significant current through this, we get a few milliteslas. So again, it's hard to even notice them unless you have very strong fields. So if you just have a lump of iron, basically the magnetic field is 0. But now what happens if we apply an external field? Let's say we apply a very weak external field. Nothing happens here. And then say we slowly increase this external magnetic field. And at some point, a domain is going to suddenly flip, where they all kind of work together and decide to flip over and line up with the external field. So like the entire domain does it almost instantly. They all kind of flip together. And, you keep increasing the external field and you get more of these domains flipping around to line up with the external field until we get what's called saturation, where all the domains are lined up with the external field. So this kind of looks like paramagnetism. So this is what it would look like when it's saturated. By this point, all the domains flipped. And so we get a significant effect here. Every domain is lined up. And so this is a pretty strong effect where everything is lined up with the external field. And again, at this point it might look similar to a paramagnet. It's the details of how it got here are very different though. The domain's kind of just one domain. They can go from whatever orientation they were in to lining up with this external field. And, different domains will flip at different times. Eventually you will become saturated if you have a strong enough external field. But there's one more crucial difference between this and paramagnetism. See, if we remove this external field, let's say we get rid of this external field, the domains stay how they are. And so now this bar of metal, like iron, is going to act like a magnet. And it is a magnet. This is, if you just have like a refrigerator type magnet, it's basically just a block of iron, typically, that's been magnetized by being placed in a strong external field. Now, there are other materials that you could use to create what we call permanent magnets. There's some rare earth materials that can create much stronger effects than we'd get with iron. But yeah, basically we have a permanent magnet here. And maybe permanent should be in quotes because it's possible to demagnetize this permanent magnet. One way to do it would be to heat it up. If you heat this up, Remember, you're adding this thermal energy which causes the atoms to oscillate more violently, and they can lose this arrangement. They can be randomized with heat. I think dropping it, if you give it like a violent shock, that could also destroy this orderly state. But typically, if you just leave a permanent magnet alone, it'll remain magnetized. So that's a very important distinction between ferromagnetism and paramagnetism. This external field will continue to exist. All right, and again, you could take an entire class on just magnetic materials. Superconductors have some really interesting magnetic properties. You might have heard of like those levitating trains and things like that. Yeah, so, but we're going to keep things very simple here. Just diamagnetism, paramagnetism, and ferromagnetism. Okay, so, yeah, and as far as a test is concerned, if anything, there could be like a multiple choice question on things like this. But, yeah, that's all we're going to cover